Okay, the streaming is on. Um, we only got 1 week's worth of classes left. So including today's lecture, we have 3 lectures left. So that'll be today, next Tuesday, and also next Thursday. Next Thursday is going to be a final exam review. So in terms of actually adding more material to the class, it's only between today and next Tuesday. So we are almost there. Okay, we got one new lab today, and the new lab is right here. It is called Structures and Pointers. So we'll go ahead and talk about the concepts that you need to know in order to get this done. Okay, so it's not. I'm even going to start with this a little bit, just so that you kind of, so I can use class time to talk about the behavior of the program that you'll be writing. So, so today's focus is going to be structures. Structures are also known as records. They're also known as class. So it depends on which class, which programming language, but they're about the same thing. So when you see something like this, struct node, blah, 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 okay, it's kind of the same thing as class node, except all the members by default are public. When you're dealing with a struct, with a class, the default is private. So besides that, basically scope control, this is just another way to define quote unquote a class, but everything is public. So are we good so far? In terms of understanding what a node is, or in this case, what a structure is. Okay. All right. So if that is the structure, um, the your homework assignment is basically implementing this particular subroutine. Not very long, right? I mean, you can actually count the number of lines, and you can even see that these 4 lines are almost exactly the same as those 4 lines. So if you know how to do these 4, the other one is pretty easy. But we do have some kind of funky stuff here. This is not a typo. We do have double asterisk, and we have double asterisk, but the plus plus applies to only the result of one of the asterisks. So this is a good test to see whether your understanding of C and C++ and operators in C and C++ is, as they say, up to snuff or not. Okay. Now, this program does compile, this subroutine does compile, and I'll even give you a full program that makes use of this subroutine in C that will compile, that will run, and you can use a debugger to help you understand how this works. Okay? So let me do that first. Okay? I'm going to go to the other class because we talked about that already in the other class. So the 2 classes are, once again synchronized, which is good because this is our last chance to have the 2 classes synchronized. So let me see where it opened a new tab. It's just hard to see. Do you guys see it? Right there? Is that it? Nope. Where did it put it? I guess it's over here. There we go. So this is the Monday, Wednesday class, and they have the code for this already, so I'm going to share that with you too. So let me go to announcements. And actually, tree main. I thought I had the C program, but that's okay. I think I still have it actually on my drive, so we can just go there. There we go. All right, so the first thing we want to do is to look at the C program, okay? So in C, this program does compile, and I will share this with you. The first thing is we pound includes standard integer.h, because otherwise we cannot use uint8_t. Then we have the node definition. So this means that anything with the type of struct node has 3 members. The first member is value, which is an 8-bit unsigned integer. The other 2 are pointers. Okay. So do you think we might have a problem with this? Having struct node L, star L, and struct node star R. And yep.
Are these nodes connected to each other?
Well, connected by pointers, it might be, okay? But in terms of members, what is member L and what is member R? What do they do? Okay, left and right, yes, but what are they? What is the type of those two members? They're not nodes, they're pointers to nodes, okay? So it's very important to understand that L itself is not a struct node. And R is also not a struct node because that would not be possible. I'm still defining struct node. I cannot have a member inside struct node that is also of the type struct node. But it is perfectly okay to have a member that is a pointer to a struct node. Is that okay? In other words, member L will help me find possibly another struct node. And that's perfectly okay. And R will help me find yet another struct node. Maybe, okay? So that's actually perfectly okay. This is the traverse subroutine that you're supposed to implement. It is structured a little bit differently. So I basically made the really cryptic statement into something that is a lot less cryptic. So we'll talk about that later. So right here we have some initializations. This is how, okay, the first line, which is a extern struct node n1, n2, all the way to n5, that's really just to tell the compiler. You will see I might make references to n1 to n5. Don't panic. I know what they are. They are struct nodes. That's basically what the extern line is telling the compiler, is saying, don't worry about these names, I know what they are, okay? And then the next 5 lines are initializations of the global variables n1 through n5. And then the 3 members of each structure is listed here. So the value is 5, L is the address of n2, R is the address of n3, and so on. Are we still doing okay so far with this code? Okay, no questions? Because if you do need some refresh of C and C++, syntax, now would be a good time to ask. No questions? So we're good? So I defined 5 nodes, okay? Some do not have any pointers, okay? So if a pointer is a 0, 0 is null, okay? N-U-L-L or uppercase is really a fancy way to say 0. So anywhere you can put null, you can also put a 0. So the reason why people prefer null instead of 0 is because null is kind of implies that it's a pointer, okay? It's a pointer that points to nowhere, and whereas 0 appears as an integer. But it's perfectly okay to put a 0 where a pointer is expected because 0 is the null pointer. Are we good so far? So 0 is one of those really weird values. You don't need to cast it to float, you don't need to cast it to double, you don't need to cast it to a pointer type. It's perfectly okay just to say 0. Okay? All right. So when we look at main, okay, this is main, which is relatively simple. So all main does is to have its own local variable, which is a. It has 5 8-bit unsigned integers. PTR, you probably want to change the names a little bit because otherwise you will end up with the same variable names in your subroutine, and that would not be good. So we can call this, the array pointer. So array pointer is initialized to A. So if you're not familiar or if you have forgotten, how C uses arrays, arrays can, when you refer to an array like this line here, APTR equals A, it is actually copying the address of A to array pointer. It is not copying the value of the array. Okay, so that's just one of those things in C and C++ where arrays are kind of special. So APTR or array pointer starts with the address of the first element in array A, and once we initialize the pointer, we just call the traverse subroutine. It doesn't print anything. So the only way to understand what this program really is doing is to use GDB, use the debugger. Is that okay? Are we good so far? Okay. So now, let's go ahead and actually run this program and see what it does. So we'll go ahead and, I got this program compiled already, so I can just GDB it. So we'll we'll put a breakpoint at the beginning of traverse. Yeah, that should be sufficient. There we go. So this is the first call of traverse from main, okay? In GDB, if you have a recursive subroutine, a lot of times you need to know, how did I get here? Were there other invocations that were recursive before I got here? So those are good questions to ask when you're dealing with a recursive subroutine. GDB has a tool to help you with that. It's called BT. BT stands for backtrace, and what it does is to show you the call stack and say, how did I get here? Well, we got here because in main on line 40 in this particular program, we only got one source code, so it's okay. So in tree.c line 40, main called traverse. And when traverse was called, these are the parameters, okay? So it shows you that pointer is really the address of N1. That's what GDB does, is when it recognizes the address of a global variable, it will even tell you, whose address that is, which is kind of handy. Array, on the other hand, is kind of like, we have no idea what array is. But if you read the source code, you will find that array as a parameter has the address of APTR from main, okay? So how do we check that, right? How do we check that array as a parameter in traverse really is the address of APTR of main? So when you use backtrace, you see these numbers here, #0 and #1. Those are called frames. And you can relocate, you can focus on a different frame. It does not change the execution point. We are still at the entry point of traverse at this point. But you can change the frame so you can actually look at things from the perspective of previous callers that got us here. So in this case, I can say frame 1, and now the context is back in main. So in main, I can print a whole bunch of stuff that only main should know about, like APTR. Let's see, did I mess up here? Actually, when I compiled the program, I was using PTR and not APTR. So that's why, if I say PTR, it will still recognize it. I know it's awfully confusing because the source code says APTR, but when I compile the program, the symbol table still remember that as PTR. So that's why there's a little bit of confusion here. Okay, this is what PTR contains, which is not exactly what I'm interested in. What I want to know is, what is the address of APTR? Now, obviously, you cannot read that either. So, so I'm going to highlight here. Hopefully highlighting it. No, does not change. Okay. It says E0D0, okay? So the last 4 digits are E0D0, which does match parameter array. So we know that, parameter array is the address of APTR from main. Are we good so far? Which itself is initialized to point to the beginning of array A. Okay? So you can double check that too, because you can say, okay, tell me what is PTR pointing to. Now we cannot see it, and then we can print what is the address of the first element of A. And you cannot see it, but they're both E0DB. Okay? So you can either take my words for it, or I can give you the source code and you guys can compile it in code blocks and play with it.
E0D0 or E0DB?
DB. So both of these are E0DB, because pointer, the value of pointer is pointing to the first element of array A in main. So this verifies that those two are the same. Now, if you only really want to know whether they are the same or not, but not really exactly what the values are, you can always check just for equality. So when you check for equality, if it says non-zero, that means they're the same. You don't need to know exactly where they're pointing to. You just need to know that they are, in fact, the same. So are we good so far with this? Okay? All right. So we can now go back. So if you do BT, you can relocate the frame anytime you want to. So you can go back to frame 0 if you want to do that. So now we're back in traverse. The first thing traverse does is to say, if you give me a pointer, okay, meaning the first argument, that is null, then I have nothing to do. Because the whole point of traverse is to say, okay, which node am I supposed to look at? Does this node point to the left? Does this node point to the right? If it does, I need to process the left-hand side, the right-hand side, and also myself in a particular order. Okay? So in this case, because the first parameter, which is pointer, is non-null, it's going to get into the conditional statement. And then it will check whether the left-hand side is null or not. The left-hand side is actually non-null in this case, which means we're going to go to the recursive call of traverse. So when we single step this traverse, we're back to traverse. So this is the part about recursive subroutines. When you're debugging it, can be confusing because now we're in traverse again. So which traverse or which invocation are we talking about? What are the parameters, and so on and so forth? To answer that question, we use BT again. So when you look at BT, this time we have 3 frames. Frame 0 is always referring to the current frame, which is the most recent frame. And then the other frames are renumbered in this case as frame number 1 and frame number 2. Frame number 1 refers to the invocation of traverse that got us here. And then frame number 2 is basically the invocation of main, which is always going to be there. Are we still doing okay so far with the process of examining what the program is doing, how we got here, and so on? Are we good? Okay. So after we get here, okay, so we can single step. PTR is non-null, but let's check out the left-hand side. Now, if you want to see the entire structure that pointer is pointing to, you can always just print star PTR. So now you can see, yeah, you can actually see it. The left-hand side is a 0 because it's really short, okay? That's a 0. So that means there's actually no left-hand side once we get here. So that's why, when we single step, it's going to skip over line 13 and it will skip to line 17 because there's no left-hand side to process for this particular node. Then what is it doing here? Okay, so we have a double dereference on the left-hand side, and then on the right-hand side, we refer to member value of the structure that pointer is pointing to. So later on in today's class, we're going to have to talk about how to get to a member that is of a structure that is pointed to by a pointer that is passed as a parameter. We'll get it done. It's not a problem. On the left-hand side, we are storing that value, which is an unsigned 8-bit integer, into an unsigned 8-bit integer that is pointed to by a pointer that in return is pointed to by array. Okay? If you know how to do one dereference, you know how to do a double dereference. Just do it again. Right? Okay. So the question is, what are we storing? Where are we storing that thing to? So maybe it helps to find out what are we storing? We're storing a value of 3. That's the right-hand side. Where are we storing it to? Now remember, array is the address of PTR or APTR, depending on which version of the code you're looking at, but it's from main. Okay, that is the pointer pointing currently to the first element of array A in main. So if array is the address of a pointer pointing to the first element of array A, one dereference becomes itself, which points to the first element of array A, right? When you dereference it one more time, it just becomes element 0 of array A in main. So doing this is going to store a value of 3 into element 0 of array A in main. Are we good so far? Well, that's the hypothesis anyway. Okay, so we'll test it. How do we test it? Well, when we test it, it really helps in order to confirm it, we'll switch to frame 2, which is main. Okay, so in main, you certainly can print a bracket 0, okay, because we are currently in the context of main. So we can say, okay, we know it was not 0 to begin with, which is good, okay, because if it was 0 to begin with, then we cannot tell whether the assignment is the thing that is causing it to become 3. Does that make sense? Okay. So now we do a frame 0, go back to the current point of execution, and single step it, okay? We just single step it. And then we do frame 2 again, switch back to the context of main, and print a bracket 0 again, and you can see it's 3. So we know that what I just said earlier seems to be true. Okay, when we store PTR points to value to array double dereferenced, we were actually in fact storing into a bracket 0 of main. Are we good so far? So this observation is important because when you are debugging your subroutine, you need to know what you should be expecting from your program that is written in assembly. So understanding the behavior of this program in C is the first step. Am I kind of clear about this? Okay. So I'm showing you the tools that can help you understand the behavior of this code in C first, so that when you try to write the code in assembly and you're debugging it, you know what your assembly code is supposed to do. Are we good? Okay. So we now switch back to frame 0 so that we can move on to execute line 18. So what is line 18 doing? Okay, we're adding 1. Okay, that part is easy. But what are we adding 1 to? We are not adding 1 to the parameter array, because adding 1 to the parameter array is not going to be very useful. We're adding 1 to what array is pointing to. Okay, hold on a second here. What is array as a parameter? It is the address of pointer in main. If array is the address of pointer in main, then dereferencing array is really just pointer in main. So we're adding 1 to pointer in main. Are we good so far? We're changing something that does not belong to traverse as a subroutine. It actually belongs to main. Okay? So we'll single step it. Okay? Or before we single step, we'll double check first. Okay? So we'll go to frame 2 again, which is main, and then we'll say print. Yeah, it's not going to be easy to see. Okay? So we'll print the address of PTR and also print PTR. And I'll just go ahead and tell you what the last 4 digits are. $11, this one here, the address of PTR is E0D0, and then what it points to, which is the value of pointer itself, is E0DC. Okay, so we'll keep those 2 things around. Frame 0 again, go back to the current frame, single step it. Okay, so if my hypothesis was right, okay, I can now go back to that frame, okay, to main, and observe that PTR itself is incremented by 1, so that it is now pointing to to element 1 of array A. Because it was pointing to element 0 of array A, now that I have advanced the pointer, it should point to element 1 of array A. Does that make sense? More or less? Okay. So, you might need to watch the video again, because, you might want to open up the source code on one side, kind of open up GDB on your own and listen to the lecture again so that you can actually correlate what I talk about in class with your own experiment, okay? All right, so we'll go to frame 2 again, and we'll do exactly the same thing as before, the address of PTR and PTR itself. So right here, the address of PTR obviously cannot change. Okay, it is still E0D0 just like in here, but the value of that pointer also has not changed. Wait, did I single step? Yeah, I did single step. That is odd. Okay, this is still spelling E0DC, which is the same as before. So pointer has not advanced by 1. That is very strange. Okay, so something is not working the way it's supposed to. Let me go back to frame 0. Array ends with E0D0, which is correct, and I'm supposed to have added 1 to that. And that is still E0D0. So the increment has not occurred. That is very strange. I cannot account for this because when we execute line 18, let me show you where we are. When we execute this line 18 by single stepping here, whatever array points to, which is pointer of main, should be advanced by 1, should be moved forward by 1. But it did not actually move it forward by 1. Okay. And we are now in a recursive call, so when you do a BT, we are now several levels up. But whatever array is pointing to did not increase by 1. It's still E0DC. That is very odd. Okay, let me finish running the program first, and then we'll see if I can find out what is going on with this program. So we'll continue execution, continue, and we are now back in main right before the return 0. So I can go ahead and print array A. So it did work correctly, even though I could not observe the pointer incrementing, but it did finish what it was supposed to do correctly. So array A is now filled with the values of the nodes, and this is what we call a in-order traversal, or a, how many people have taken 430? CISP 430? 1, okay. So this is an in-order traversal. Let me see if I can explain that.
So when we increase the pointer in main, are we going to the next location in RAM? Or?
We are moving the pointer of main to go to point to the next element of array A in main. Okay. So I'm not really sure why the debugger is not showing that pointer is advancing the way it's supposed to. So right now it is showing E0, E0. So it did increment. Oh, I know why. I think I know why. Because I was looking for a change of the least significant digit, and that's not what it did. It did change. So this one is E0DC, and before it was E0. It was a DC too? Because it can jump by a few bytes, instead of 1. I cannot account for this. This doesn't, it doesn't seem to make sense to me. Okay, let's run the program again. Okay, so I'm gonna quit, and this time I'll compile the program again. Okay. And we'll put a breakpoint. Okay, list char first. And we'll put a breakpoint on line 18, which is the one that I have in question. Okay, so we'll run the program. Okay, so print what is array. So the value of array is E0D0 at this point. What is it pointing to? It is E0DB. Okay, so we'll go ahead and single step, which should change star array to E0D1. Okay, and we'll print it again. And it says E0D, oh, E0DB, and now it's E0DC. So it did advance. Okay, I brain fart.
Is it possible
Big time.
when we did the breakpoint last time, we were relying too late, so we didn't see the change?
Or maybe I just had a brain fart and I forgot that it was E0DB and now it's E0DC. So maybe I just forgot what the letter was in hexadecimal. But it did advance, so it did work the way it's supposed to. Okay, because I like things, I like mysteries, but at the same time, this when something is supposed to work, it seems to work, and I cannot explain why it works. That gets a little frustrating. So it was just a brain fart, okay? So the pointer did change. The problem is, we can't really see the number very easily when I have a dark color, to display the hexadecimal digits. So it did work, okay? So this is what the program does. So now the question is, what do you have to do to implement this program? So let's go back to the source code here. And then we'll go ahead and open up a window in assembly. Okay, so I'm gonna get rid of this. This was an example for my Monday, Wednesday class. Now you guys are more than welcome to also watch the video of the Monday, Wednesday class. If you think, oh, I can use another example to illustrate how this is all done, you can go ahead and watch that one too. Okay, so the first question is, how do we implement a structure in assembly language? Because assembly language has no high-level concepts like a class or a structure or record. So this is how we're going to do it. Okay, we'll do it by a whole bunch of labels. The first one is node value is defined to be 0, and then we'll define node L to be node underscore value 1 plus, and I'll explain what these labels are representing once I'm done writing this stuff here. And then we have node size being node underscore R 1 plus. Okay, so I'm gonna go back and explain what these things really are. So what each label, or the first 3 labels, are representing is an offset, okay? It's an offset of a particular member of a structure from the beginning of the entire structure. Do we have any questions about that statement? Node value, node L, and node R are basically just labels so that we can use a symbolic name to refer to the offset to a particular member of a node. Yep.
So we're going to have essentially what is an array of...
Nope. The array is an array of
nodes?
bytes. We have 5 individual nodes. Okay, N1 to N5 are individual nodes. It is not an array. I could have done it using an array as well, but I did not.
So when we create the node, are we going to basically decrement D 4 times and then have the values next to each
We'll
other?
look at that code. I will give you the main. I would have translated this main also, and give it to you as well. So your job is really only to implement traverse. Yep. But I want to explain these, step by step. So node underscore value is the offset of member value in a struct node from the beginning of the struct node. That's basically what it is. Okay. So if you want to look at this from a C perspective, this is what it really is. Okay. You're looking at. I can't do that because I don't have an actual struct node to look at, so I can't really do it. So I'll just have to kind of write it in the usual way. Offset to member value from the address of a struct node. That's basically what it is. Yep.
So if you give us a pointer to a node,
Mm-hmm.
in order to find the value, the offset would be 0. But in order to find the, for instance, node right, it would be...
1 byte off.
Okay. Well, node right would be 2 bytes off.
Yeah, right would be 2 bytes off. Left is 1. Yep.
So you're going to give us, and this is how we're getting to the, what is it, the members of the structure?
Yep. That's how we get to the members.
Offset.
Yep.
Gotcha.
Go ahead.
I'm sorry, could you explain again why, like, we have a struct inside of a struct that's the same name? Like, what did that cause?
We don't have a struct inside a struct. We have a struct that is being defined, which is node, but the members L and R are pointers to nodes. They're not nodes. In other words, from one node, you have the address to find another node, but it is not having a node inside a node. So those two are entirely different concepts. You cannot have a node inside a node. That is just not possible because you're still defining the structure. So now, if you look into a node, it also has another node, so it becomes an infinite, quote unquote, infinite recursion. But it is okay to have a node that has a pointer to another node because a pointer is always the same size. Every pointer is only 1 byte wide. If it's a pointer to a node that is huge, the pointer itself is only 1 byte in TTP ASM. Is that okay?
So we're basically just, like, defining the type of the pointer?
Say that one more time.
We're basically just defining the type of the pointer?
So the type of L is a pointer to a struct node. The type of R is also a pointer to a struct node. Now, if you remove these asterisks, the compiler will bark and say, you cannot do that because it doesn't make sense in that case. But with the pointers, it's perfectly okay. So are we doing okay so far with the first three definitions? Node value, node L, and node R. Are we good? Okay. So node size is not a displacement to a particular member. It's telling me how big a node is. Okay, because I will need to know that if I need to allocate local variables that are of the type node, okay, which, in the program that you implement, you don't need to do that, okay, but it's handy to know the size of a node in case we need to allocate for local variables. So are we good so far with how we define, quote unquote, define a structure in assembly? Okay. All right. Yeah, go ahead.
To define node size, were you going to go over that?
So the definition of node size is the offset to the last member of a node plus the size of that member. Because node R itself is
That's the displacement from
yes.
the pointer, but what is node size?
Node size is how many bytes a struct node will take up.
If a node didn't have a left or a right, the node size would be smaller than if it had.
If you change the corresponding struct so that you don't have L and R, then obviously it'll be like just 1 byte long. Each structure is 1 byte long.
Right.
But in this case, each structure is 3 bytes long because we have 1 byte for value, 1 byte for L, and 1 byte for R. So that's why in this case, the size of a node is 3 bytes.
Gotcha.
Okay. So are we still doing okay so far? More or less? Okay. All right. So now, instead of giving you the code to implement traverse, I'm going to give you the code to do something, that may be just as useful. Okay. If you're actually doing a program in object-oriented programming, you will probably need something like that. Okay. So I'm going to call this one Init Node, initialization of a node. Give me a node, and I will initialize it. Okay. So we can basically just say initialize it with some constant values. Okay. So we'll go ahead and see how we can do it with constant values. So we'll just say PTR points to value is always 255. Okay. Instead of 0. Okay. It doesn't really matter. Okay. And then L is 0, and L is 0, R is also 0. Okay, so this is what we want to do. So the assembly code to do this, okay, I can show you the assembly code to do init node. So init node is going to have one parameter that is on the stack, and then we have the returned address also on the stack. And at the entry point of the subroutine, the stack pointer is pointing to the return address. Okay, so that part should be pretty much the standard now. I mean, without even me mentioning it, you guys should have this picture already. So you have to remember the pointer PTR is not a struct node. It is a pointer to a struct node. Okay, that is a very important distinction with or without the asterisk. Okay, so now the question is, how do I get to the value of the structure that is pointed to by PTR? Okay, that's the question. So what should be my starting point? Okay, forget about the 255. That's super easy. So if I need to figure out the address of the value member that is part of the structure pointed to by PTR, where do I start?
Start with a return.
No. Well, okay, I see what you mean by. Yeah, we need to get the pointer first. Okay, so using our usual way of doing things, return address is going to be 0 because we don't have any local variables. And then PTR is going to be return address 1 plus because it is a parameter. It is pushed before the return address, and therefore it has an address that is higher then the return address. Okay.
LDI.
Okay, so we need a LDI, pick
C,
some register,
yeah, any register with pointer C
okay.
or A.
Mm-hmm.
Then add A and D. Yeah.
Yep, so at this point, A is the address of our parameter. Then what do we do?
Well, we have to dereference it.
We need to dereference it. Okay, very good. So we need to dereference A at this point because, oh, okay, good
So
job.
LDA.
LDAA, right?
But we have to do that twice, right?
No, not yet. We do it once first. Okay, so let's see what's happening here. So if we do a LDAA, A becomes the dereference of the address of PTR, which is just PTR itself, right? So if I dereference it one more time, I get to the content of the structure. But is that what I want?
Not yet.
Not
So
yet.
we have to do it 3 times, right?
No, not 3 times.
The offset.
We need to.
Increment, right? Increment the pointer that A has.
No.
Well, we want to copy it into.
Okay, so right now PTR is pointing to the address of a entire structure.
Right.
What I want is one of the members of the structure. So what do I do to get to the address of a particular member when I have the address of the structure in register A already? Add the offset of the member, right, to the address of the structure. Yep.
We copy the pointer to another register. That way we still have that same.
Well, we have 2 more registers to play with, so we have enough registers to do this. So what we need is to use another register, let's say register B, okay? You can use register C too, that's both of those are fine. So we're going to load node underscore value, in this case, into register B, because that is the offset. So B is now the offset from the address of a struct, okay? To the member value. Okay? So now we got everything ready, right? So an add AB will get it done. So A is now the address of member value of the structure the pointer is pointing to. Is that okay? So when you're reviewing this stuff here, okay, you might want to draw a picture, okay? Draw a picture of what A is pointing to in all of these steps, or what A is representing in all of these steps. Yep.
If I wanted to keep A pointed to the first, or the node's address, can I
Uh-huh.
add? Can I switch?
Yeah, you can add
Add.
BA.
So
Then-
B would become the.
Yep, you can certainly do it that way because that's actually a good way to do it because we need the address of the pointer again and again. Yep. So that's a good way to do it. So if that is what you prefer to do, then you can say that. Okay, we just need to change the comment so that B is the one that has the address. Okay. So you're going to use all of the registers, aren't you?
No, just.
Oh, you're going to end up using all of the registers because we cannot. You're right.
Just use store.
Yeah, so register A is free now, so we can reuse register A. So now we can do LDIA with the right hand side, the right value, the R value, and then we can now store to B, where B is pointing to A. But I cannot trash A because the whole idea of add BA is to keep A around, so we have to use register C. So we do end up using all the registers.
But that's fine because we're allowed to.
Yes, we are. Yep. But we're doing some optimization here, which is good. Okay, it's good in the sense that, sorry. We are preserving code and it will execute faster because we are not recomputing things over and over again. Yep.
Why did we pass 255 to C instead of like a parameter?
Instead of a parameter, what do you mean?
Initializing.
Because we are trying to implement this thing here. The right-hand side is just a constant of 255, and we have to put it into a register before we can store it into a location of RAM. because the st instruction is the only instruction we have to modify a location in RAM, and it needs whatever value you want to store to be in a register first. I know some people are tempted to do something like this, but it won't work. There's no such addressing mode in this particular processor.
Can't do that in the opcode anyway.
Exactly. Well, the architecture has no pathway to do it. If you look at the architecture, there's no pathway to take a constant that is an immediate as a part of the instruction and store it also to the location pointed to by one of the registers. The architecture itself does not support it. Yep. Simply does not work. Okay, so now we're done with the first line. The second line and the third line at this point would be pretty easy to do because register A is still PTR. Okay, so we still got that around. So that means from here we just have to change B to member L. Okay, and add BA. So now B is the address of member L of the structure the pointer is pointing to. And then we can now just say, okay, we know what to initialize it to 0. So put the 0 into register C, STBC. Okay. The next one is even easier because we just have to say, well, where do we find R? Okay, we still have to do this part. And then we don't even have to reinitialize register C because we also want to store a null pointer into R. So C is already 0. So that's why this code is a little bit easier now. Yep.
When we do this function,
Mm-hmm.
should we write our own initialize node function?
No, there's no need to do it. No, it's already initialized.
Because you're giving us.
I'll give you the code that has the global nodes already initialized, so you don't have to do any initialization. I'll explain what you'll be given with. Yep.
Won't A always increase?
Huh?
Just thinking A is the offset right when you're doing add B and A?
Well, A is constant. A is still just pointer, which is the address of the structure itself. We are using register B to refer to the address of the member that we want to initialize. So you are correct, okay? If you know the sequence of these members, you can just keep incrementing, B instead of recomputing B and adding stuff like that. But if you just increment B, to get to the next member and then the next member, if I change the definition of the structure, your code won't work anymore. So the idea of doing it this way is so that it is insensitive to the ordering of the members within the structure. Is that okay? So there are this kind of optimization is okay. Even if I change the member ordering within the structure, this code will still work.
It's using labels.
Because it's still using labels. And we are recomputing the address of the member, repetitively, which is okay. But if I just rely on the fact that, value is the first member, L is right next to it, and then R is right next to L, and just increment B instead of recomputing B, that code will no longer be insensitive to the definition of the structure. So is that point understood? Okay. So we want to do optimization, but only to the point where it is still okay if I change the structure itself. So this is all done. Okay. So the initialization of a node is done. So now it is time to return. The stack pointer stays put the entire time. So this time, so we don't have to mess around with the stack pointer too much. So we have an LD. Okay, we can use register A this time because Init Node does not return the value. So we can use register A. So we use LD AD, increment D to deallocate the return address, and then the JMP-A to go back to where we're supposed to go back to. So that concludes the subroutine init node. Init node is not needed by the program. Okay, I'm just using it as an illustration of what we need to do. Are we good so far? Yes? Okay, cool. All right, so I'm going to show you what you'll be given with, with this program. So you'll be given with this code here, okay, which is written entirely in C, and you can use GDB to debug and step through the code so that you know what your program is supposed to do. Okay? So I will give you this code. I will also give you tree.ttp asm, which I think is somewhere, but let me go find it. Oh, it's tree main, there we go. So I will also give you tree main.tp. Okay, let me show both of these side by side because it's kind of important to do that too. Okay. All right, so this is the assembly code that is given to you, and this is the C code that is also going to be given to you. All right, so we'll focus on main first. Okay, so here's main, and this is the assembly main. There we go. So in the C code main, we have a local variable A that has 5 bytes, and then we have a local variable A array pointer, which is a pointer to an 8-bit unsigned integer. So in assembly code, we just have a whole bunch of decrement, 6 of them, right? Because we need 5 for the array, and then 1 extra one for the pointer itself. Okay, and we also give those label names. Okay, instead of using A, which is confusing because in assembly programming we have register A. So some people in the Monday Wednesday class said, oh, why don't we use something else like array as the name of the array itself. So that's why I use array here, which is also not a very good name because you have the parameter array in Traverse. So you might want to change array to yet another name. Okay. Yeah, so you guys can make that change, or you can change the name of the parameter in Traverse. Okay, so you can do either way. So what is following here, okay, is the initialization of APTR. Line 14 and line 15 together is computing what? I intentionally left out the comment just so that you guys have to kind of work on it a little bit to figure out what is in register A when line 15 is done. The address of array, the address of array in this case, but A in the C code. Okay, so that's the right hand side of the assignment. So we got the right hand side of the assignment done by line 15. Line 16 and line 17 is computing the address of APTR, or array pointer itself. So once we have the right hand side in register A, the L value, or the address of where we need to store the value in register B, a simple store will finish the operation. So are we good? Okay. So in summary, lines 14 to 18, okay, battery just kind of, this is why we have rechargeable batteries. For the longest time, the lab people did not want to use rechargeable batteries because they were afraid that they might get lost. People may toss it into the trash can not knowing they're rechargeable. I haven't lost a single cell yet. So lines 14 to 18 implements array pointer gets A in C. Okay, so the next one is really just the call. Okay, the call is to call traverse with the address of APTR, which is a local variable, and also the address of N1, which is a global variable. Okay, so this requires a little bit of explaining. So we'll skip forward in the assembly code to see what is the equivalence of these initialization of the global variables N1 through N5. So the initialized nodes N1 to N5 in C code is implemented like this in assembly code. Okay, it's really quite literal, right? So N1, okay, in C becomes N1 as a label in assembly. Because as global variables, they start existing from the time the program starts to run. So they do not need to be allocated. They do not need to be initialized in any code. They just simply start to exist. Yep.
Where are they stored? Are
They're stored in RAM. They're right after the halt instruction.
Really? So
Yeah.
it's on the upper side, like where the program
Yep.
is.
Mm-hmm. Now, when you're talking about an actual C program, they actually have a different place to put all your global variables. But in assembly language, in a very simple architecture, we just kind of interleave your global variables with your code. So they're living within the same space, basically. Okay. So the way we initialize N1 in C is we want the value to be 5, and then we want the L member to be the address of N2, and then we want the R member to be the address of N3, and that's what we do with line 44 to 46. Now you can see that on line 45, we simply refer to N2, not the ampersand of N2, because N2 as a label is defined to be the address of whatever is right next to it. So N2 is, as a label, is the address of a byte already. So you don't need to use ampersand to say that we want the address of, because the label is defined to be the address already. Are we good so far? Okay. Yep.
So these are all stored in RAM, but how do we get the address of N1? Because that is
You just refer to N1.
you could just refer to the label
Yep. Yep.
in
Yep. So when we
because it's global, right?
because it's global. So when we go back to the actual code corresponding to the call to traverse in assembly, so line 20 to line 23 is what is pushing the second argument. Now that one is, we have seen it a lot already, because between line 20 and 21, we're computing the address of APTR, right? And then line 22 and line 23 is just pushing that on the stack. So line 20 to line 23, no mystery. We have seen that already in the swap subroutine. Okay, the swap subroutine has to push the address of one of the local variables, and that's how we compute the address of a local variable. So what about the global variable N1? Even easier. Just LDI A comma N1, because N1 as a label is defined to be the address of the first byte of that structure. So you just load A with N1. You don't have to worry about, but we got an extra byte on the stack at this point. But guess what? N1 is not relative to the stack pointer at all. It is a global variable. It's not living on the stack. So we don't have to account for that one extra byte here. So once A has the address of N1, we just push it on the stack, and that ends up pushing the address of N1 on the stack. The rest, from line 29 to line 32, very typical, invocation sequence of instructions. Push the return address, and then just go to the subroutine. When we come back, we increment D twice to get rid of the two arguments on the stack, and then on line 37 to the halt instruction, we are simply deallocating all the local variables. There are two local variables, the array, which has 5 bytes, and then the pointer itself, which is only 1 byte. So I can deallocate all of them in just like 2 instructions. Yep.
Are the labels not case sensitive? Because on 25 you have lowercase.
They're not case sensitive. Labels are not case sensitive in assembly. All right. So let's go ahead and assemble this code. Okay. There's one thing I need to do because your traverse is currently undefined. So I can just say traverse and do nothing. Okay. So when you guys get this file, you will need to kind of fill it in with your code. Huh? Oh. Well, I like it spelled that way. And then we'll let the compiler or the assembler to complain about it. It's good to check the compiler, the assembler once in a while. Isn't that a little early? All right. No, it won't work. I need to get rid of the other stuff here. Okay. it should complain right there. So it complains, it doesn't complain about the definition, but it complains about the reference to a label that is currently not defined because it doesn't know where the problem is, okay? So the only point where it can complain about is when we make use of a label that is not defined because it cannot associate and go like, hey, you got a label that spells almost like this, and this word is in the dictionary, the other one is not, maybe you meant that, okay? Maybe at some point the assembler will be able to do that, but not right now. So right now it just complains. Okay, fine. So you just go to the label definition and say traverse, okay? Now the complaint should go away. Let me see. Oh. What did I do? What did I do?
Control Z.
Control Z. Then. Yep. So we'll give it a moment. There we go. So we're good. All right. But the important thing I want to show you is in the Assemble tab. So in the Assemble tab, I want to show you how the global nodes are really initialized, which is right here. Okay. So N1 as a label is defined to be location 37 or 25 in hexadecimal. Okay. When you look at N2, okay, N2 is actually more interesting because it is referred to. So when you look at N2, boop, 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 it is at location 28 in hexadecimal. So you can also see how 28 is utilized here, which means the L member of N1 is the address of N2. So are we making the association, of how the labels are defined and how they are used as members or the values of certain members of another structure? Is that good so far? Okay. So this code is doing the main, is also doing all the global node initialization for you. And I'll give you this code, okay, as a starting point. So the C code, I'll give it to you. The assembly code like this, I'll also give it to you. So you just really have to implement traverse. Okay. So I do have a few ideas of how to implement traverse. So let's go back to traverse. And I have some suggestions, okay, of how to do this. Traverse is obviously recursive, okay? So the first thing you want to do is to make sure that you can make it work not in a non-recursive way, okay? So what you do is you cut out a lot of stuff first, okay? You cut out, oops, this. In other words, you're cutting out everything that makes it recursive, and with only that much left to do. So that means if you give me a node, if pointer points to an actual node, I'm going to take the value of that node, put it to the byte that is pointed to by a pointer, which in return is pointed by array, and then I'll advance whatever array is pointing to by 1, and then I'll just return. Okay? If you can get this to work first, okay, then you can move on. If you cannot get this to work first, focus on this part. Are we doing okay so far with this? Okay. So how do we know what this is supposed to do? This is why we have the C code. Okay. So the C code is here to help you because you can make a modification to the C code and run the C code through the debugger to understand the behavior of the modified C code. So you can implement this in assembly first. Are we good? So if you give it a null pointer, okay, if this is null or 0, then it should skip everything and not do a single thing. So you have to check that as well. Are we good so far? How do we check that? How do we check that if I give it a null pointer, it would actually in fact do absolutely nothing? Well, you just go to the assembly code that I gave you. And, okay, not this one. This one. Okay, so you go to this code that I have already given you. So instead of passing N1 or the address of N1 to the subroutine, give it a 0. That's a null pointer. So in that case, it should not modify the pointer in main at all. And it should not store anything into the array that is a local variable in main. So that's how you can test whether that part of the code is working or not. So switching back to the C code. So let's say you get this part done already. You can retrieve the pointer, check whether it's null or not, and if it is not null, you will perform these operations and you check that those operations are done correctly. That is like more than 60% of the work that you need to do. Okay? So then what you do is you do not uncomment every single thing. You just uncomment one side of the recursion, but leave the other one commented out. Because if as soon as you try to implement the recursive call and then your program doesn't work anymore, then you know that this code here or the logic implemented this code is somehow not working correctly. Okay? So if you do it this way, you also have to understand that the algorithm will not do the same thing as what it did before because it's no longer traversing the right-hand side. So you can run this code, okay, as it is now in C through the debugger in C first. Understand the behavior of what this is supposed to do, and then implement the code in assembly and then see if your implementation in assembly is resembling what it is doing here. If it does, then you have 99% of the code done, because the other side is really a mirror copy of the first part. Okay, the only difference is instead of referring to member L, we're referring to member R. But otherwise, the structure of the code is identical. So that would be the order that I will use to implement the program, is to do it step by step. You get rid of the recursion first, implement all the basic stuff, add one side of the recursion, make sure that works first, and then add the other part. Go ahead.
So will this, it'll traverse left, and if it can't traverse left, it tries to traverse right, and then it will traverse left again?
Correct. Okay, so let's see what is the time. Okay, we got 10 minutes. We got plenty of time. So what I'll do is I'm going to give you a kind of graphical representation of how the nodes are traversed, so that it's just a visual way of looking at it. Okay. Let me see if I already. I think I got a Zerno open already. But that is not what I can display. It has to do with a union issue, and I cannot disclose those. Okay. There we go. All right. So the way it is represented is we have N1. N1 has a value of 5. And then we have N2 and N3. So N1 points to N2 using its L member. It points to N3 using the R member. So is this okay? Does everybody understand the notation? What is the value of N2? I think it's 3. Let's check.
We haven't had a chance to look at it yet.
Yeah, that's okay. Yep. So N2 is 3, N4 is 4. Okay, so let me switch back here. So N2 only has a right-hand side because its left-hand side points to nothing. So it only has a right-hand side pointing to N4, where the value of N4 is 4, the value of N2 is 3. N3 only has something it only points to the left-hand side, has nothing on the right-hand side. Let me see, is that right? N3 itself has a value of 10. And what is the value of N5? 9. There we go. Oops. Okay. So this is N5. It has a value of 9. So I'm going to kind of block out the value, just so that it's easier to see, which part is the value, like that. Okay. So this is a kind of graphical representation of how the nodes are pointing to each other. When you do not see anything here or here, it simply means those pointers are null pointers. Are we good so far? So this traversal algorithm is called a in-order traversal, which means I only do something about the node itself when after I process the left-hand side, but before I process the right-hand side. Okay. So let's see what's going to happen here. We start with N1, right? So let me pick a different color and a slightly different size. So this is what we start with, okay? And we always want to look at the left-hand side first if there is a left-hand side. N1 does have a left-hand side, okay? So we go here. N2 has no left-hand side. So now so basically, it tries to go to the left-hand side, except there's nothing. So now we are between processing the left-hand side and processing the right-hand side. So that is the time when 3 is put into the array, okay? And then, when we look at the right-hand side, we go like, yep, it does have a right-hand side. Okay, good. We go to the right-hand side. We get to N4. When we are at N4, we try to go to the left-hand side. N4 doesn't have a left-hand side. Then we go back to N4 and go like, okay, now we're in between processing the left-hand side and the right-hand side. That is when we put the value of N4, which is also 4 in the array. After we put the 4 in the array, now we go to the right-hand side of N4. We go like, okay, what is on your right-hand side? Nothing. Okay. So at that point, we have processed N4 completely because we have explored the left-hand side itself and also the right-hand side. When it's all done, we go back. Okay, that's when we return to the previous invocation of traverse. So now we go back to N2. So I'm going to put a label for here. So when we get back to N2, that is between processing the left-hand side and the right-hand side from the perspective of N2. So that is, no, we're done because we just returned from the right-hand side. We are all done. And then we go back to the first invocation. So this is 4, this is 5. So when we get to step 5, that is in between the left-hand side and the right-hand side from the perspective of N1. That is the time when we put the value of N1 into the array. So the array now has a value of 5 in A bracket 2, basically. Are we still doing okay so far? Okay.
Well,
Yep.
how did we get from 3 to 4 and then not go back to 4 again?
Because when we get back from
Back to 3.
Because when we get back from 3 to 4, we are returning to
We just processed the right side and we're returning from that.
Well, I got that, but like, how do we not do it again?
he just said it.
Because after you process the right side, you're at the
There's no code after the right side.
If you look at the code, the function, the last part of the function. Is the
Okay,
right
I can
side.
show line numbers too. So when you look at line 26 to line 29, when you return from line 28, there's nothing else to do. Lines 20 to line 23 says, let's process the left-hand side, if there's a left-hand side. Lines 26 to line 29 says, let's process a right-hand side, if there's a right-hand side. But between the left-hand side and the right-hand side, I'm going to put my value into the array. I'm going to append my value into the array.
I guess I'm not so much concerned about the C as the assembly, and I guess I'll ask that in the lab. 'Cause
The assembly code just has to mirror the logic of the C code. So if you get the C code, you will know what your assembly
get
code
back
is
to you
supposed to
on
do.
it in the lab. I'll
Okay.
get back to you on it in the lab.
Okay.
I don't want to hold this up.
Okay. So we are now at step 5, which is between processing the left-hand side and the right-hand side from the perspective of N1, and that's why we append the value of N1, which is 5, into the array. So after that, we go to the right-hand side of N1. So this is step 6. At step 6, we go like, well, N3, do you have a left-hand side? N3 says, yep, I do have a left-hand side. So now we go to the left-hand side of N3, which is N5. And then we ask N5, if you have a left-hand side, go there. I don't have a left-hand side. So now we're in between processing the left-hand side and the right-hand side from the perspective of N5, which is when we append the value of N5 to the array. Then we process the right-hand side of N5, but N5 has no right-hand side. So now we're done with N5 because we have processed the left-hand side itself and the right-hand side of N5. So now we go back to N3. When we go back to N3, now we are in between processing the left-hand side and the right-hand side from the perspective of N3, which has a value of 10. So that's when we append the value of 10 into the array. And then we ask N3, do you have a right-hand side to process? Nope, I do not. So that means N3 is now all done. And then it goes back to N1, and we'll call it step 8. But at this point, N1 would also have the left-hand side processed, itself processed, and then the right-hand side processed. That is when we return from traverse back to main and basically conclude the execution of your part of the algorithm. Is that okay? Yep.
How do we get access to like the values, like the value, the left side and the right side in assembly?
In assembly?
Because when you initialize it, you just say byte.
Right. Okay, so it depends on what you're referring to. So if you go to the that's just the initialization. Let me find the other one. Okay, so this is the C code. So this is the initialization, and this is why we know 5 is the value of N1, 3 is the value of N2, because the first member of a struct node is the value.
But how do we, like, because you know how when we did the example one, we initialized it with like node underscore value to say that's the value of the node. How do we know from this? Like when we want to...
You should never refer to N1 to N5 because these are global variables. So from the perspective of the subroutine that you need to implement, which is traverse, okay, so let me go back to the C code here. So from your perspective, I think your question is, how do we know what is the value of the structure that the pointer is pointing to? You just have to use, so your code to access this is very similar to the code that we use to initialize members of a structure. Instead of a write operation, you have a read operation. Is that making any sense? No? Okay. It's okay. So, okay. So now we can look at Init Node and Traverse at the same time. We explained how to do this, right? Which is taking whatever the right-hand side is and overwrite whatever the left-hand side is, right? So in your code, you have to do the reverse. You're not overwriting a member of the structure. You're reading a member of the structure. Is that okay? Okay. So the first thing you need to do, if you're going to implement this in assembly, the first thing you need to know is what the stack looks like from the perspective of main. Okay? Where is the pointer? Where is the array? Because those two are the things that you have to focus on, basically when you're debugging your code. You have to make sure the pointer is advancing, and you have to make sure that the array is getting filled up. So the first thing you need to do is to say, okay, based on the main program and the way I define the labels and also the way I initialize or change the stack pointer, this is where the pointer is, and this is where the array is, because you have to focus on those areas to make sure that your program is working correctly. Any other questions? Yeah? Oh, don't have a question? All good? Okay. All right. So we're going to end, okay, we are right on time. So this is going to be the end of today's lecture. I will put it online as soon as possible, and then we'll go to the lab and get started with this lab. I will send the files to you right away too.